Hi, everyone. Welcome to Chapter 2. Chapter P, we build some of the very basic rules of algebra. And in Chapter 1, we spend a lot of time solving equations and inequalities. And we're going to finally learn to use all of these equations and inequalities and properties here in Chapter 2. So in Chapter 2, we eventually want to work our way up to functions and then all the various properties of functions. But we're going to take a couple sections to get there, but that'll be 2.4. Until then, we have 2.1, 2, and 3, all pretty nice, just kind of establishing what graphs are. So let's start with the plane. So the coordinate plane, as you've seen it in the past, or also known as the Cartesian plane, is kind of like a second dimension number line. What we've done in chapter 1 and even before that is we had just a single number line for all of our answers. We had say that x equals 5 is the answer, or x is greater than -3 is the answer. All of those answers, all those solutions sat on just one single x line. However, what we now want to eventually get to is using a coordinate plane, where not only do we have an x part of the solution, we also have a y part of the solution. So in a way, the coordinate plane is kind of like a second dimension number line, but don't necessarily need to think of it that way. We're just working our way up to 2 dimensions. So we have a horizontal line in our coordinate plane and a vertical line. That horizontal line we call the x-axis. Well, that's pretty nice, right? We just talked about a real number line. We had answers that were x's. So that horizontal line is called the x-axis. The right half of the x-axis we define to be the positive x direction, and that kind of makes sense. And then the left half would be the negative x direction. Like I said, this kind of makes sense because when we read left to right. Well, if we're reading left to right, that's kind of how x values run. They run negative to positive. We like it when things go up. Likewise, we have a vertical line called the y-axis. So not only are we going to get things with x's, we're going to get things with x's and y's simultaneously. The upper half of the y-axis is the positive y direction, and when the lower half is the negative y direction. Well, horizontal is kind of intuitive in this way because we read left to right and things increase as we go left to right. However, even though the y-axis is kind of intuitive, up means positive, down means negative, it's a little backwards because we read negative to positive left to right, but negative to positive will be up to down. So in other words, up is positive, right is positive, left is negative, down is negative. These two axes meet at what we call the origin, which has the coordinate point 0, 0. And we're going to spend a little bit more time in just a moment actually graphing coordinate points. So here is the coordinate plane. You see the x-axis that runs left to right, y-axis that runs up and down, and you see these y values are positive, these y values are negative, these x values are positive, these x values are negative. Like I was saying, we use coordinate pairs coordinate points or ordered pairs of the form A, comma, B. So this is the same notation that we use for open intervals, right? Kind of saying everything from A to B, A not included, B not included, but we're going to use the same notation to do something different now, where A comma B is some point in two-dimensional space. A is our horizontal location, the x coordinate. B is the y coordinate, or the vertical location. So if you're trying to figure out where some A comma B goes to, you would go to the left or right coordinate for A and up and down coordinate for B. So for example, some random AB right here, A would be the horizontal distance, B would be the vertical distance. And here you see the origin at 0, 0. Okay, well, quadrants, well, if you notice here, do you see that these two lines create 4 divided areas? We have the area above the x-axis and to the right of the y-axis, left of the y-axis and above the x-axis, and so on. Each of these 4 things are called quadrants. So going from the top right and working our way counterclockwise, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. And even if we don't spend a ton of time looking at that here in algebra, you will definitely look at it in pre-calculus. So quadrant 1 would be all the locations where x and y are both positive. Quadrant 2 would be every location where x is negative but y is positive. Quadrant 3, both x and y are negative. In quadrant 4, x is positive, y is negative. So let's do some graphing. Let's graph these 6 points here. Well, let's start with just one. Let's start with 3, 1. 3, 1 says we go 3 units in the positive x direction and 1 unit in the positive y direction. Or in other words, 3 is positive, go right 3, 1 is positive, go up 1. Well, negative 2, 4, if this is positive 3, then negative 2 would be 2 units in the opposite direction. So negative 2, 4 would be 1, 2 units to the left, but still 4 units up. 1, 2, 3, 4. Negative 3, negative 4 says we're going to go 3 units to the left, 1, 2, 3, and also 4 units down, 1, 2, 3, 4. Okay. 2, negative 3 says we're going to move 2 units in the positive x direction, 1, 2, but then we're going to move 3 units down, 1, 2, 3. Negative 3, 0 says we're going to go 3 units in the negative x direction, 1, 2, 3, and we're going to move 0 units up and down since we have negative 3, 0. 0, 5 says we're not going to move left or right at all, but then we're going to go up 1, 2, 3, 4, 5 points. Okay, so I'm trying to break this down into as formal terms as possible in terms of describing it for a college level algebra class. However you have graphed points in the past, whatever is easy for you to remember, by all means, keep doing it that way. Well, what if we want to take the distance between any of these 2 points? Maybe not so hard to say from this point to this point is 3 units, but how about going from this point to this point, or even this point to this point? Well, that's where we come up with distance. We can draw a line from the origin to any point on the graph. So let's say we have the point 3, 4, and we want to draw the line from 0, 0, the origin, to 3, 4. Okay, well, this line is the distance between 0, 0 and 3, 4. But how do we find the length of this line? It's not quite that obvious. It isn't just 3 plus 4. This isn't 7 units. Okay, but what we can do is we can make a triangle with this line right here. We can go bottom leg right here. We can go upper leg, or side, however you want to word it, right? We can go this leg right here and this leg right here. And now the question is, what are the values of these 2 legs? We have a formula to tell us, the distance of this leg. We have a way to relate all 3 legs. But what is the distance of this leg? What is the distance of this leg? Well, very conveniently, you see that this leg has 1, 2, 3 units. Oh, that's the x coordinate. And you see this vertical leg has 1, 2, 3, 4 units. That's the y coordinate. So the horizontal leg has length A, or the x coordinate. Vertical leg has length B, the y coordinate. And then we say that diagonal line, the actual distance, is the hypotenuse. And we define it to have length C. Now, we relate A, B, and C using what is called Pythagorean theorem. You've probably heard it in the past. It's got some very funky applications in pre-calculus, but for here in algebra, very simply, it is A squared plus B squared equals C squared. The length of the horizontal leg squared plus the length of the vertical leg squared equals the diagonal's length squared. Okay, so if we want to find the length of that line, the hypotenuse, well, if we have the point 3, 4, then A is 3 and B is 4. So all we're going to do is plug info in to A squared plus B squared equals C squared. Well, A is 3, B is 4. We know how to square numbers. 3 squared is 9, 4 squared is 16. We know how to add. 9 plus 16 is 25. And we know from here, in chapter 1, we would take the square root of both sides, get plus and minus. Square root of 25 is just 5. But for the purpose of talking about distance, distance should always be positive. So the length of that line that we drew before from 0, 0 to 3, 4 is 5 units long. Now, this is great and dandy, but what if we want to find the distance between any 2 points and not just the origin? Well, if we combine the general distance formula, if we combine Pythagorean theorem with the one-dimensional distance formula, absolute value of a minus b or absolute value of b minus a, in total, we can jump to its definition. If you have 2 points, x1, y1, and x2, y2, the distance between them is this right here. Now, you already see some squares. You see a square root. You also see this x2 minus x1, kind of like b minus a. So there is both Pythagorean theorem and the distance formula we had in chapter P. So putting that all together, we get here. It takes a little too long for us to derive, but I think you guys see the elements here. So if we want to find the distance between any 2 points, we're going to just plug things into x2, x1, and y2, y1. So let's find the distance between -2, 5 and 3, -4. Well, x1, y1 is going to be our first point. So x1 would be -2 and y1 would be 5. Likewise, q would be our second point, 3, -4. So x2 is 3 and y2 is -4. And what we're going to do is just plug in all of this information for x2, x1, y2, y1. x2 is 3, x1 is -2, y2 is -4, y1 is 5. 3 minus -2 is +5. -4 minus 5 is -9. 5 squared is 25. -9 squared is 81. And square root of 25 plus 81 is square root of 106, which is roughly 10 units. So the length of the line that connects -2, 5, and 3, -4 is roughly 10 units long. Okay, but also I want to stress that our choice for x1 and x2 doesn't matter. Intuitively, you're probably going to just use first point is x1, y2, second point is x2, y2, but I just want to show you that it doesn't matter. It doesn't matter how we define one or the other. So if we instead let 3, -4 be x1, y1, x1 is 3, y1 is -4, and then x2, y2 would be -2, 5, x2 would be -2, and y2 would be 5. So let's again plug in all of those numbers. x2 is -2, x1 is 3, y2 is 5, y1 is -4. -2 minus 3 is -5. 5 minus -4 is +9. -5 squared is 25. 9 squared is 81. Oh, and look at that. We're right back to where we got. So you're most likely going to use the first point to be x1, y1, and second point to be x2, y2. But if you're ever feeling a little funky, you're more than welcome to change it up. Okay, let's find the distance between 3, 3, and 6, 6. Well, you're probably thinking 3 and 6 are 3 units apart, so the answer must be 3 units. Let's see why that's not true. Okay, first point, let's let that be 3, 3. In that case, x1 would be 3 and y1 would be 3. Let's let the second point be 6, 6. So x2 is 6 and y2 is 6. So we're going to plug in all that information to this formula right here. x2 is 6, x1 is 3, y2 is 6, y1 is 3. 6 minus 3 is 3. 3 squared is 9. 9 plus 9 is 18. But 18, square root of 18, square root of 18 is 3 square root of 2. So the distance between 3, 3 and 6, 6 isn't as simple as just, oh, it's 3 apart for x's and y's, so the whole answer must be 3. No, the distance between 3, 3 and 6, 6 would be roughly like 4.2 units, since square root of 2 is 1.41. So just be careful for that. Doing this with some very ugly negative numbers, let's let -2, -1 be x1, y1. x1 is -2, y1 is -1. x2, y2 would be -7, -3. So x2 is -7, y2 is -3. All right, let's plug in everything we know. Now just be very careful. -7 minus -2 would be -7 plus 2. So this is -5. -3 minus -1 would be -3 plus 1, or -2. Negative 5 squared is positive 25. Negative 2 squared is positive 4. 25 plus 4 is 29. Okay, see, not a negative in sight in our final answer. Okay, well, let's go back to doing Pythagorean theorem on the same 2 points that we started with. We said the distance from 0, 0 to 3, 4. We got our answer to be 5 using Pythagorean theorem, but that means we should also get the same answer doing the general distance formula. Well, x1, y1 would be 0, 0. X1 would be 0. Y1 would be 0. X2, Y2 would be 3, 4. X2 would be 3. Y2 would be 4. Well, plugging in everything we got, well, conveniently, subtracting 0 doesn't change anything. 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. Square root of 25 is 5. Oh, how nice. Exactly the same thing. So Pythagorean theorem is very nice when we're doing it just from the origin, but in any other case, you're probably more likely to just use the distance formula. So in the past, I've actually done baseball research. There's a video of it out there somewhere, probably unlisted. But what if we want to extend this to the real world and actually do something with something that we're familiar with? So let's talk about baseball a little bit. So on a normal Major League Baseball stadium, and even on some Little League stadiums, or Little League fields, I should say, consecutive bases are 90 feet apart. So here we have, home plate is, let's say it's 0, 0. Well, it takes us 90 units to get to first base, 90 units to get to second base, 90 units to go to third base. But now what I want to know is how far apart are opposite bases? How far apart is home from second? How apart is third from first? Well, you see 0, 0, and 90, 90, and you want to be like, well, it's 90 units, or even it's 180 units. But not quite. If you were to throw a ball from home plate to second base, throwing it 90 units would be over here. Throwing it 90 units would be over here. That would not quite match to get to second base. So let's figure out how far that is. Okay, home plate is at 0, 0. Second base is at 90, 90. So just find the distance. That's all we're looking for. Well, we would have 90 minus 0 plus 90 minus 0. 90 squared plus 90 squared would be 2 90 squareds, right? X plus X is 2X. Well, this is 90 square root of 2, which is roughly 127 feet. So that throw from home plate to second base would be 127 feet, or likewise from third to first would also be 127 feet. So get out of the idea of just looking at, 0 to 90 is 90, 0 to 90 is 90. Answer must be 90. It's a little more convoluted than that. Well, let's talk about one more thing here in 2.1, and that is midpoint. So midpoint, as it sounds, is literally the point equally distanced from two others, the point in the middle of any 2 points. If we're using the same x1, y1, x2, y2, well, this would be our formula. How do we find the point in the middle of any 2 things? Well, take their average. Add the x values together, divide by 2. Add the y values together, divide by 2. So let's find the midpoint of negative 3, 6, and 1, 4. x1, y1, negative 3, 6. x1 is negative 3. y1 is 6. x2, y2 would be 1, 4. x2 is 1. y2 is 4. So what we're going to do is add the x values together, divide by 2. Add the y values together, and then divide by 2. So negative 3 plus 1 over 2, 6 plus 4 over 2. I have these out of order. I just realized that. Okay, negative 3 plus 1 is negative 2. 4 plus 6 is 10. So negative 2 divided by 2, negative 1. 10 divided by 2, 5. Okay, that's really not all that surprising at all. Very nice. Okay, 820 and 1123. Well, x1, y1, x1 would be 8, y1 would be 20, x2, y2, x2 would be 11, y2 would be 23. So we're going to add the x values, add the y values, divide each of those sums by 2. Well, we just get 19 over 2 and 43 over 2. That's it. Nothing crazy. No need to find decimals. In my classes specifically, I prefer fractions, but somewhere around you guys might prefer decimals. Okay, find the midpoint of -6, -17, -12, -15. Alrighty, well, we're going to add the x values, -6 plus -12, comma, -17 plus -15, both of them divided by 2. Well, -6 plus -12 would be -6 minus 12. -17 plus -15 is like -17 minus 15. -6 minus 12, you're $6 in debt. You spend another 12, you are now $18 in debt. -17 minus 15, you're $17 in debt. You spend another 15, you are now $32 in debt. -18 divided by 2 is -9. -32 divided by 2 is -16. Okay, so not all that crazy for midpoint. I actually think it's pretty nice. A little less careful work than distance, but of course, always be careful. And kind of like for distance formula, your choice for x1, y1, and x2, y2 doesn't matter. Okay, well, what if the pitcher's mound is the midpoint between home and second base, which at an actual baseball field, it isn't quite, but let's just say it is. So how far is the pitcher's mound from home plate? Alrighty. Well, so let's say we have 0, 0, and 90, 90, and we want to find the midpoint for them. That it's between 0, 0, 90, 90. On a real baseball diamond, it's not actually halfway between 0, 0, and 90, 90, but let's pretend it is. Well, midpoint, we're going to add the x coordinates, add the y coordinates, and we're just going to get 45, 45. So then, how far apart is the pitcher's mound from any other base? Okay, well, so like I said, it's not actually in the middle of the diamond, but we're just saying it is for this example. But now let's find the distance from the pitcher's mound to third base. We haven't used third base at all in this section, so let's use it here. Okay, let's check from third base, which is 0, 90. And again, now, if we're asking how far apart the pitcher's mound is from third base, this is the distance formula. Subtract the x coordinates, subtract the y coordinates. -45 squared plus 45 squared is negative 45 squared would be positive 45, and then we would get 2 times 45 squared, or 45 squared of 2, which is roughly 64. I believe on an actual diamond, the pitcher's mound is 60.5 feet away from home plate, but in our imaginary baseball example, that's how far pitcher's mound is from any base. Okay, and that's actually it for 2.1. Chapter 2 in general is very, very long. So we're going to go section by section. We're going to do a lot of different things. So it's a lot of different information, but take each section on its own. So with that said, I will see you in 2.2. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.